Everyone, I'll go through the solution of homework 7. Many have asked me to, if possible, to go through it in a recorded session. Unfortunately, I couldn't find a room, and I think it's better to get it done earlier. So I'll do it in a recorded on my tablet. Okay, so let's start with the first question. So let G be a finite group and N is a normal subgroup of G. Show that if H is a subgroup of G mod N, then pi N inverse of H is a subgroup of G. And the size of pi N inverse of H is H times N. And here, of course, pi N is the projection from G to G mod N. That sends an element G to the coset Gn. Okay, so let's prove that. So let's prove it. So the fact that pi N is a subgroup of G containing, well, pi N is a subgroup of G has been shown in class. The inverse image of a subgroup is a subgroup under any homomorphism, not necessarily pi N. And we will need that detail since the coset N is a subset of H, which is a subset of G mod N, then N, which is the kernel of pi, is a subset of pi N inverse of H. So pi N inverse of H contains N. And hence, pi N of pi N inverse of H is equal to pi N inverse of H mod N, right? This is the definition of pi N. Because if, let's say, A is a subgroup of G, and N is contained in A, then pi N of A is just A modulo N. Now, on the other hand, pi N of pi inverse of H is just H. This is because pi N is surjective. This is really a set theory property. It doesn't have to do with homomorphism. And hence, we just look at the sizes. Oops. Mod N. Now, since all of these groups are finite, and therefore I've used the fact that if f from A to B is surjective, and y is a subset of B, then f of f inverse of y is equal to y. Okay, now let's move on to the second question. So suppose that G is a group and S is a set, and suppose rho from G to symmetric group on S is a group homomorphism. Show that the following defines an action of G on S. I take G star S to be rho G applied to S. Indeed, rho G is a function on S, right? So rho, if G is in G, rho G is a function from S to S. Okay, let's prove that. So now let S be in S. We have first to check that e.g., well, let's write it in there. So rho G is a function from S to S. Really? Okay. Now, first, we need to show that the identity fixes everything. So let S be in S. What is E G star S? This is just rho of EG star S. Or sorry, this is just rho of EG of S. Now rho of EG, since rho is a homomorphism, rho of EG is just the identity function on S, because a group homomorphism takes the identity of G to the identity of sim S. So what's the identity on sim S? It's the function, it's the identity function that sends everything to itself, that sends every element to itself. Great. Now let G1, G2 be in G. What is G1 star G2 star S? This is just G1 star. What is G2 star S? This is just rho of G2, which is a function on S applied of S. And by the same argument, well, by the definition, this is just rho of G1 applied to rho of G2 applied to S. The notation may be confusing here. But rho of G is just a function. Oh, it's a bijection, but it's a function. So this is just rho of G1 composed with rho of G2. These are functions on S, applied on little s, of little s. Now, since rho is a homomorphism, this is just rho of G1, G2 of S, which is by definition G1, G2 star S. Hence, star defines a group action. Okay. Great, let's move on to the second exercise of G on S. Okay, so let G be a group and H a subgroup of G. Let S denote the set of conjugates of H. Show that the following defines an action of G on S, and that the stabilizer of H is NGH, the normalizer, and deduce that NGH is a subgroup of G, and show that H is normal in the normalizer. Let's prove that. So first, note that if G is in G, if G and X are in G, then G, X, H, X inverse, G inverse is just G, X, H, which belongs to S. Now, let X be in G, and G1, G2 be in G. What is EG star an arbitrary element of S? This is just EG X8 star XH X inverse, which is just EG X inverse, EG inverse, which is just XH X inverse. So the identity acts trivially, or it doesn't change. When you act with the identity, you don't change the element of S. Great. Now let G1, G2 be in S, in G, sorry. Well, I do have it. So what is G1 star G2 of XH X inverse? This is just G1 star of, when you have it from here, this is just G2XH, G2X inverse, which is G1, G2X, H, G2X inverse, G1 inverse, or in other words, this is just G1, G2X, sorry, this is just G1, G2, X, X inverse, G1, G2 inverse. I mean, we could have just kept it this way. We could have just written it this way. Let me fix that. Okay. Which is just G1, G2 star XH X inverse. Hence, star defines an action of G on S. Now, what is the stabilizer of H? The question asks me to find the stabilizer of H. Stab H. H is an element of S, right? Like, so H is an element of S, so it makes sense to talk about the stabilizer of H. Is an element of the G set S. H is an element of the G set S. So what is the stabilizer of H? So it's set G and G, such that G star H is equal to H by definition of the stabilizer. This is G and G, such that GH, G inverse by definition is equal to H. And this happens to be the normalizer of G and H. Now, I've expressed the normalizer as a stabilizer of an element under an action. And we know that the stabilizer is a subgroup of G. The stabilizer of any point in the G set is a subgroup. So stab H is a subgroup of G, and hence NGH is a subgroup of G. Now we want to show that H is normal in NGH. So what we show really is that let H be in H. Let H so first of all, let's show that H is a subgroup of NGH. What is H? H inverse, this is just equal to H. So H belongs to NGH. So H in fact is a subset of NGH. And to show it's a normal subgroup, what do we need to show? We need to show let's say Y be in NGH. And X be in H. What is Yx, Y inverse? We need to show that Yx, Y inverse belongs to H. So Yx, Y inverse of H times Yx, Y inverse. What is that? This is just Y, X, Y inverse. Oops, I'll run out of space. Let's see. This is just Y, X, Y inverse. Y, X inverse, and then Y inverse. Well, if Y belongs to NGH, then Y inverse HY is just H. And then, yeah, so, and then the same thing again and again. So if X belongs to H, this is just H. X inverse is equal to H. And Y belongs to NGH again. So this is just H. This is one way of doing that. So H is a normal subgroup of NGH. Here, of course, I use that if Y is in NGH, then Y inverse is also in NGH. Okay. Now I move on to another question. So let G be a group, and in a normal subgroup of G, show that G acts on N by conjugation, and that the set of fixed point of this action is N intersection G. So first of all, what is conjugation? It's a function from G cross N to N, since N is normal. It's Gn, G inverse. Let me write here for a better use of space. First, let's justify why Gn, G inverse belongs to N. That if G is in G and N is in N, then Gn, G inverse belongs to N, since N is normal in G. Okay, let's show this as an action. So, let G1, G2 in G, and N in N. What is EG star N? This is just e.g. n e.g. inverse, which is just n. So the identity acts trivially on any element in n. That's the first property. And what's g1 star g2 of n? This is just g1 star g2 n g2 inverse, which is just g1 g2 n g2 inverse g1 inverse, which is just g1 g2 n g2 inverse g1 inverse, which is equal to g1 g2 n g1 g2 inverse, which is just g1 g2 star n. So this is indeed an action. So star. So G acts on n by conjugation. Okay, now what is the set of fixed points? Recall that n is in n is a fixed point. Let's call this action star. If and only if g n g inverse, or if, let's do it more generally, if and only if g star n is equal to n for all g and g. If and only if, well, what is g star n? This is just g n g inverse is equal to n for all g and g. If and only if gn is equal to ng for all g and g. If and only if n belongs to zg. Now, since n belongs to n, we can say that if and only if n belongs to zg intersection n, right? Because n already belongs to n. Okay. Hence, the set of fixed points of this action is n intersection zg. Okay, let's move on now to the third question in group action. Let G be a finite group and H a subgroup of G of index P, where P is the smallest prime divisor of G. Show that H is a normal subgroup of G. Now the idea here is to express H as the kernel of the homomorphism. So we will express H as the kernel of the homomorphism induced by the action of G on G mod H. So what is the action? This is just G star XH is equal to GXH, the regular action of G on the set of left cosets. Here G mod H, when I write G mod H, is a set of left coset. It's not necessary that H is normal. Okay, great. Now, what do we do here? Now, I mean, we can use the result immediately. We know that n intersection, the kernel of this coset representation, is just the intersection of the conjugates of H. It's contained in H, is a normal subgroup of G. And the index of n divides p factorial in that case. This is the theorem from class. Okay, now G mod n also divides G. So the index of n divides G and p factorial. So the index of n divides GCD of G and P factorial. Okay, now what is the index of G and P factorial? What is the GCD of these two? Really here it's just a small number theoretic. I mean the idea here that the GCD will be P, exactly P. Why is that? I mean if Q, if Q is a prime divisor of P factorial, which is P times P minus 1 times 1, then since P is prime, then Q is less or equal to P, right? Because, yeah, the largest prime divisor of P factorial is just P. Now also, note that P squared does not divide P factorial. So really the only common factor of G and P factorial is P. Because any prime divisor of G is P or more, and P squared cannot divide doesn't divide P factorial, so the GCD doesn't contain the squared. So the GCD of G and P factorial is just P. Now, since P is prime, Gn is 1, or Gn is P. Now it can't be 1, since n is contained in H, and H is different than G, since H has index P bigger than 1. So n is different than G. Now, so hence, we have that the index is P. Now n is contained in H, and since the two indices are equal, so the size of n is equal to the size of H. So n is equal to H. Since n is normal, it's the kernel of the coset representation, kernel of coset representation, or you can show it from then H is normal in G. Okay, now let's move on to the third exercise. Let G be a group and let G be in G so that the function lambda G from G to G, x to Gx is an element of sim G. Now we have done this in class, but I mean let's do it. We can show it's injective or surjective, or we can just write an inverse. So I mean, you know, what would the inverse be? Let's do it with an inverse. Lambda G inverse composed with lambda G of x. What is that? This is just G inverse. I'll do it quickly. Of Gx, which is just x, and lambda G. I mean, here we can switch the order of G and G inverse. It's just G inverse x, which is just x. So lambda G inverse is an inverse, or the inverse in that case, of G, of lambda G, and hence you know that the inverse of a function is unique if it exists. So lambda G belongs to sim S. We should know that the function is bijective if and only if it has an inverse. Great. Now show that the function from G to sim G that sends little g to lambda G is a group homomorphism. Yeah, I forgot this. It's an injective group homomorphism, and deduce that G is isomorphic to a subgroup of sim G. This is Cayley's theorem, really. We've done this in class, but I've put it again in the homework. So what is phi of lambda G1, G2? This is just lambda g1, g2. All I need to check is that whether this is equal to lambda g1 circle lambda g2 composed with lambda g2. And let's do this. So let x be in g. Here let x be in g. To show that two functions are equal, I just need to evaluate an arbitrary point and show that these two functions are equal at this arbitrary point. So what is that? This is just lambda of g1 applied to g2 of x, which is just g1, g2 of x. Let's write it this way. Hence, phi of g1, g2 is lambda g1, g2, which is by this equality here, just lambda g1 star circle composed with lambda g2, which is just phi of g1 composed with phi of g2. The operation in sim G is composition of function. So phi is a group homomorphism. Now to show that phi is injective, let's look at kernel of phi. We show that the kernel, we remember that the homomorphism is injective if and only if the kernel is the identity. Okay, let's do this. Let's show this. So lambda gx, so let g be in the kernel. Then lambda g is the identity function on x. Or lambda g is the identity function on g. So lambda gx is equal to x for all g and g, for all x and x, for all x and g, and hence gx is equal to x for all x and g, and hence by cancellation g is equal to eg. Now we know that the identity is always contained in the kernel, since eg is contained in kernel of phi. Then ker phi is just eg. Okay, this is Cayley's theorem, and hence by first isomorphism theorem, G, which is isomorphic to G mod Eg, which is equal to G mod ker phi, is isomorphic to rho of G, which is a subgroup of sim G. This is Cayley's theorem. We've seen this one in class. I put it as a small refresher in the homework. Okay. Now suppose that G is a finite group and let G be in G have order n and n. We know that n divides G and hence G is an M for some m and n. Show that lambda G can be represented as a product of m disjoint cycle of length n each. Okay, so here, you start with let H, I gave a hint afterwards to look at the coset of this subgroup. So let H be in G. H has order n since G has order n. And the size of the set of left coset are m. So there are m left cosets. So let's H1, Ag, H2, Hm and G be a representative of the distinct cosets of H, distinct right cosets, So, so this is this notation I used for the set of right cosets, or oops, this is just HH1, which is just H because it's one identity, HH2 up to HHM. Okay. Now let's write down the permutation lambda g as a product of disjoint cycles and see what happens. Well, the idea here is just to start somewhere, but let's start by the identity. Now, where does the identity go? Identity goes to, so lambda g of eg is just g. So identity goes to g under lambda g. And g will go to g squared. And g squared will go to g cubed. Okay, let's and g cubed go to g fourth, and so on. I reach gn minus 1, and gn minus 1 will go to g times gn minus 1, which is gn, which is eg, since g has order n. Great, now I pick an element that does not appear in here. Well, I start with h2. Where does h2 go? Goes to to gh2. I repeat the same thing, gn minus 1 h2. And gn minus 1 h2, when I times it by g on the left, it will go to gn times h2, which will go to h2. So this is a cycle. And so on. h3, gh3, gn minus 1 h3 dot dot dot, and then hm up to gn minus 1 hm. And all of these cycles have length m, and there are n of them. So really the cycles here are just kind of the cosets, if you want. It cyclically permutes. If you write these in order, it will cyclically permute the elements of the cosets, provided you write them in this order. Okay, great. So lambda g is a product of, there are m cycles of length n each. Okay, now let's look at the fourth question. Now let G be a finite group of order 2k where k is out. Show that G has a normal subgroup of size k. How do we do that? Well, we'll have to use the previous part. So 2 is a prime dividing G. 2 is a prime number dividing the size of G. By Cauchy's theorem, G has an element x of order 2. Hence, lambda x is a product of k cycles of length 2 each. So lambda x is a not product of transpositions. Is a product of an odd number of transpositions. Hence, lambda x is an odd permutation. Right? Now, how do we show that this has a normal subgroup of size k? Now, so what do we do here is that let rho be the map from G to sim G. And sim G, since G is finite, is a finite set, to be the sign homomorphism. This is phi from question 1, plus or minus 1. And rho is just the sign composed with phi. So rho of G is the sign of phi of G, which is the sign of lambda G. It's clear that rho is a homomorphism, since rho is the composition of two homomorphisms. And rho is surjective, since rho of x is minus 1, right? Because it's an odd permutation, is sine of lambda x, which is minus 1, and rho of the identity in G, which is sine of lambda the identity, which is always, well, the sign of the identity function on G, which is always 1. Hence, rho G is equal to plus or minus 1. This is the group plus or minus 1. And so, by the first isomorphism theorem, G mod cur rho has the same size as rho G, has size 2. So G divided by the size of cur rho is 2. So cur rho has size k. And cur rho is normal in G. Okay. Now let's move on to exercise 4. This one is a bit long, but it's not very hard. The first question, find an isomorphism. You really don't have to justify your answer here. From Q8 to ZQ8 to Z2 cross Z2. Okay, so let's prove this. Let's do that. So what is Q8? Recall that Q8 is just the quaternions, plus or minus 1, plus or minus I, plus or minus J, plus or minus K. We know that I squared is G squared, is K squared is minus 1, and IJ is equal to minus JI is equal to K. Okay, so what is ZQ8? We've shown that ZQ8 in a previous homework is just plus or minus 1. And we know that ZQ8 is normal, so Q8 is normal in Q8. The center is always normal. And we have seen before that the cosets, really the representative of the cosets, are just ZQ8, I ZQ8, J ZQ8, and K ZQ8. Okay, so here any coset has order 2. Any element here has order 2. Those have order 2, as you have seen in another homework. This has order 1. So this is a group of order 4 where every non-identity element has order 2. So this is isomorphic to Z2 cross Z2. You can check that. And then here, you can just permute them and it will magically work. You don't have to justify that. But yeah, this is what you needed to do. Let's pick this one. I mean, I think you have 6 possible homomorphisms here. Isomorphisms. Okay. Let's do one more. This one is interesting. You don't have to justify, but find 5 non-isomorphic groups of order 8. And I'll justify quickly here. So let's do this. And you know, you have the abelian ones. Z mod 8Z, Z mod 4, Z cross Z mod 2Z. And then you have 3 copies of Z mod 2Z. And you have non-abelian ones, which is D4 and Q8. So these are abelian. The idea is to find a feature of one that is not in the other. Okay, great. Now for the abelian ones, I mean, it's clear that they're not isomorphic, but let's find a feature. So here the maximal order of an element. In Z8 cross Z8, it's cyclic, so what's the maximal order of an element? It's 8. Z4 cross Z2, the maximal order is 4, if you take 1, 0, namely. And abelian, and Z mod 2 cross Z mod 2 cross Z mod 2, the maximal order is 2. So no two of these three are isomorphic. No, so now, I mean, you know, we can still write here, this is 4 and 4, but doesn't matter. And now here, let's look at the number of elements of order 2. Now, once I've shown that these are not isomorphic, I don't need to look at that. So how many elements of order 2 does D4 have? It has 5 elements of order 2. Orbital reflection and rotation squared. So R squared and all the reflections have order 2. And Q8 has only 1 element of order 2. So really, no two of these groups are isomorphic. Okay, great. Three, classify up to isomorphism the groups G for which there exists a surjective homomorphism from G to Q8. Okay, now so let's do this. So I mean, really what you're looking for is to classify. I mean, you know, you have if rho is a surjective homomorphism, if rho from Q8 to G. If rho from Q8 to G is a surjective homomorphism, then Q8 mod rho is isomorphic to G. So now what we have to look for, since rho could be any normal subgroup, we know that a subgroup is normal if and only if it's the kernel of a homomorphism. This amounts to classifying. So to say how many isomorphism classes do we have? The quotient groups. Q8 mod n, where n is a normal subgroup of Q8. Now, what are the normal subgroups of Q8? We've seen this before. Q8. All the subgroups of Q8 are normal, right? We've seen this in a previous assignment. We've seen the diagram of the subgroups of Q8. It's this one. Now, so if you take n, if n is I or j or k, all of these are normal. Every subgroup of Q8 is normal. We've seen this in a previous homework. Then Q8 mod n has order 2, and any group of order 2 is isomorphic to Z mod 2Z. And this is, if you will, the center of Q8. Now, if n is equal to plus or minus 1, by the previous question, is isomorphic to Z2 cross Z2. And more trivially, if n is Q8, Q8 mod n is isomorphic to 1, the group 1. And if n is 1, Q8 mod n is isomorphic to Q8. So up to isomorphisms, there are 4 quotient groups of Q8. Z2, Z2 cross Z2, 1, and Q8. Okay, thank you everyone, and I hope this helps.